Everyone. So today we're going to jump to chapter 9 in the digital electronics part of our class. So we're actually skipping chapter 8 and jumping into chapter 9 on binary logic and logic gates. And we're actually, this week we'll cover chapter 10 also, because chapter 10 is where we actually start building circuits with these logic gates, because otherwise you don't really have a lab to do next week. So, and these are two very short chapters. I think the first 3 sections of each of the chapters are the important ones. So combined together, it's actually shorter some of the other longer chapters. Okay, so let's talk about what digital electronics is. When people talk about digital electronics, I think about fingers because these are my digits, but it should really be named binary electronics because the 10-base system is actually what our fingers are based on, the decimal system. Okay, and these systems are called numerations. It's just a system that we use in order to account for value of something, right? So when I say the number 12, right, it's in decimal and not in a different numeration such as hexadecimal or something like that. And that's what's the commonly used. And those of you who have taken like a computer programming class or a binary logic class, this will be a lot of review, but hopefully you will still get something out of this. It's just, my version of it. So let's all, and I try to be as close to the book as possible. And that way we're all speaking the same numeration and nomenclature. So that way everything's clear. Okay. So in decimal, right? So decimal is what we typically use, what we grew up with. When I say 1, 2, or the number 12, right? It represents basically 2 times 10 to the 0 power, 1 times 1 to 10 to the 1 power, and then there's a bunch of zeros in front of it, let's say, right? And then 0 times this, 0 times that, and all is base 10 system. Okay, when you add this number together, anything to 0 power is 1. So this is actually 2 times 1 plus 1 times 10, right? Plus 0, right? And when you add these two numbers together, that's how you get 12, right? And then here I'm gonna put a little subscript there, 10, to tell you that this is a decimal base numeration that I'm using. Okay, you can represent the same number, okay, in binary numeration. Okay, that same number is actually 1, 1, 0, 0. Okay, and this time I'm going to put a 2 there. In the future, you're not going to see the 2 because when you're dealing with computers, the default is actually binary, not decimal. Okay, and this number, right, is the same as 0 times 2 to the 0, just like what we did before, but instead of putting a 10 there, you put a 2, right? And then 0 times 2 to the 1, 1 times 2 to the 2, 1 times 2 to the 3, okay? And then we're not allowed to use 2, 3, 4, 5, 6, 7, 8 because it's a binary system. The highest number a single bit can hold is 1. You can either only have 0 and 1 because that's the maximum value you can add. Okay, if you add these numbers together, this is the same as 0. Anything with 0 in front is just 0, right? You don't have to calculate the exponent. And then 1 times 2 to the 2, which is actually 4, right? And then 1 times 2 to the 3, which is actually 8, right? And that gives you the actual number 12 in decimal. Okay, and binary electronics is actually the easiest way to do math because you're only dealing with 1 and 0. You don't have to carry is 5 divisible by 3 or 6 divisible by 4 and all that stuff. It's just always 1s and 0s. There's and if we were brought up in binary, I think the human race will actually be a lot smarter, and it'll make math a lot easier for a lot of people, actually. Okay. In electronics, it's also the least noisy and the easiest way to do math and record values, and that's why it is the basis of all computing and electronics in the binary electronics or digital electronics. Okay, I know I don't like the word digital electronics, but that's the one that's we're kind of stuck with. Okay, so why is the this binary system the easiest and least noisy way? Not just because the math is easiest in binary, but in electronics we also have very easy way to represent binary values. Okay, so back in chapter 7, before we jumped into here, the last thing I cover is actually a comparator and a Schmidt trigger. Remember how those function is that the idea is that, you have some threshold that you want to, if it's above some threshold, you want the output to be true. If it's below some threshold, you want the output to be false, right? And then, so this is a analog signal. This red is analog, right? While here in blue, close enough to blue, I guess. I think that's more blue. Okay. Right here, the output of the comparator or the Schmidt trigger is actually the binary version of it, because you have, some voltage representing 0, and you have some voltage representing ones or true. And in this case, this is probably going to be a 5-volt. And so how does binary logic work, right? So we use voltages or current to represent these binary numbers instead. So we're representing ones and zeros with some voltage, okay? So in the previous example, 5-volt means 1. You also will see either it's called high or true, okay? 1, high, and true, they all represent the same state, where an output of, not 5-volt, 0-volt, right, represent a 0 in binary number, or low, okay, or false, okay? So those are all equivalent things, and true, okay? And depending on which logic family you're using, these could be switched around, so be a little careful, okay? So here is a little table. So most of the time in this class, we're going to be using TTL logic. So if you want to represent, 0 in binary, the range of inputs and output are here, because, right, as you see in your analog electronics, right, what happened is that, you get close to, sometimes you get something that's, 0.001 volt, and I just tell you that's close enough to 0, right? And so we actually have a little bit of a room, right? And it's actually built on top of these Schmidt triggers. Remember, these little thresholds has 2 different thresholds that you can build into it, right? So if an input is between 0 to 0.8 volts, so up to 0.8, so if it's 0.81, right, then it's actually in an unknown state, okay? It represents a 0, but if it's output from a device, it has to be between 0 to 0.5 volts. So this way you also have a little bit difference between them. Okay, anything above 2 volts, right, or up to 2 to 5 volts, right, that represents a 1. For output, anything between 2.7 to 5 represents a 1. Okay, so this is a TTL logic. It's a particular sets of values that everyone agrees to. If you're using TTL 5-volt, this is actually TTL 5-volt, then these are the values you have to design your circuit to be in order for it to conform to that logic family. There's also CMOS. This is 5-volt CMOS. I'm not going to go through all the numbers again. ECL is actually a current-based logic system. So these values here are actually could be different depending on what the voltage, what the resistor you put at the end of the ECL is. But mostly just focus on TTL, and then when you need to use a different logic family, You just have to figure out, oh, what's the translation to that, okay? And your circuit is built a little bit differently, but the logic works the same. Just to note that there are also low voltage TTL. So low voltage TTL goes from 0 to 3.3 instead of 5 volts. Those of you who are older, well, not you guys, none of you guys are older. People coming from my age, USB, the universal serial bus, used to work from 0 to 5 volts. And then when they converted to this newer micro USB, they converted to low voltage TTL, which goes from 0 to 3.3 volts instead. Okay. There's also low voltage or 1.8 volt CMOS, which is actually kind of cool because they specify the maximum voltage there, which I like a lot more than low voltage. What does low voltage mean, right? And ECL, as I mentioned, actually is the false and true state is actually 0 and 5 milliamp current. So it's a current driven. The state is actually set by current, not voltage, and the voltage changes depending on what resistor you put at the end of it when you measure it, right? So the ICs we've been using in this class in your lab is the 74LS, which is actually a 5 volt TTL. And when we convert to FPGA, we actually have to deal with CMOS. But for now, let's think of everything in terms of 5 volt TTL, okay? But before we can get into the binary gate, right, we're going to have to do a little bit of review or introduction of arithmetic in binary. So as I said, binary arithmetics are actually easier if we were to grow up with it, but we didn't. So therefore, we have to always translate back to decimal. So for integer, okay, everything can be stored in non-negative powers of 2s. So for example, if I wanted to represent the number 21 in decimal using binary instead, this is an 8-bit unsigned integer. Hopefully I get this right. Okay, as you saw before, right, the way you calculate this, you're reading this backward actually. So you're reading right to left. Okay, so which is opposite of what we're used to once again, right? So this one here tells me that it has a value of 1. The next one is the 2's place because 2 to the 1 power, but we know that number is 0 anyway. The next one is 4 because that's 2 to the 2. Okay, so you add 4 to that. The next one is 8, but you add 0 anyway. The next one is 12, not 8, not 12, 16, right? Because 2 to the 4 power, which is in the 5th place, right? You always subtract 1, get you there. And the rest are 0, so you don't have to worry about it anyway. Okay. Okay, so then 16 plus 4 plus 1, that gives you 21 in decimal. Oops, not 0 in decimal. Okay. So notice that I don't write the 2 there anymore, right? So by default, right, all the numbers are represented in binary. Okay. Okay. This is a way to represent an integer, specifically non-negative integer. We're going to have to deal with the negative sign in a second. But the book also mentions that we can represent floating point values. But this utilizes negative exponents. And the book says, oh, it's just complicated. It's just a little bit extra step in complication. But I do want to show you what that's like. And you're going to notice that, oh, the binary values of it is exactly the same. The logic works exactly the same. So we're just going to stick with integer to teach you the logic. And then, when you have to deal with floating point numbers, you just have this additional step of converting it into floating point of, 16 bits or 64 bits or 32 bits, depending on what you're using. Okay. So let me just show you how a computer actually represents, or electronics actually represent, a 16-bit floating point. So this is, if you ever do programming, when you do float, A equals to 32.1 or something like that. This is actually what's happening inside your hardware. Okay. So since this is a 16-bit number, there's going to be 16 ones and zeros. Up to 16, well, always going to be 16 ones and zeros. The first bit is actually a sign bit, so it tells you, oh, this is number positive or negative. Okay. All right. This is the last bit, which is actually the most significant bit. And I'll speak a little bit more about that in a second. Okay. The one on the right, so remember we always start transcribing from the right to the left, right? These are fractions, okay? And then we use 10 bits to do that. Well, for a floating point number. And what that does is that it tells you some fraction that's going to be less than 1. Okay? Okay. Because the biggest number here, right, is 2 to the negative 1, which is actually 1/2. And then the next one is 1/4. The next one is 1/8 plus 1/16. And those of you who know your, what's that called? Harmonic series? Oh, I remember the name. Right. Know that this number, as you go to infinity, if all these are 1s, approaches the maximum value of 1. Okay, that's why it's called a fraction. It's not exactly a fraction, but it's a series of fractions that you add together. Okay, so in this example, if you did all this computation and find all the 1s, right, and then add all these numbers together, okay, you end up with about 0.7. Okay, okay. Then what you do is you add 1 to it, because 2 to the, I don't know why they just don't write 1 here. You add 1 to it, okay. Then you multiply that by what's known as the exponent part of your floating point number. The exponent is calculated by whatever this exponent is, right? In this case, it's 19. Okay, the biggest you can actually get to is 31 because it's 5 bits. Okay, and then you do a little bit of math with it. You have a little bias, and then you convert that into basically the bias exponent. In this case, it converts it to 4. Okay. Okay. Right. So you put that 2 to the 4 here. So 2 to the 4, right? It's 16. Okay. So you take 16 and you multiply by 1.6972665, blah, blah. Right. You get 27.15625. Okay. And then the bit actually gives you the negative sign front. Okay. And that's how your computer or hardware you're using are actually calculating these floating point numbers. Okay. So this is just a way for the number system, the numeration, to represent numbers that are, fractions of fractions of 1s, and then also have numbers that are bigger than 1 in front of it. Okay. So the largest number you can represent using these floating point is actually 2 to the 16 minus 1. So 65,000 something. Okay. But what that does is that since this fraction, right, you're only using 10 of your bits to represent the fraction, the precision of it is actually about only 10 to the minus 5. So if you're doing like Excel spreadsheets and you're calculating your taxes and you're rounding everything to the cents anyway, you don't actually care about this, right? So that's why most computer systems use this, and saves a lot of space. If you were had some programming class or play with these binary numbers before, you also know something called as a double. Okay, a double is basically what's known as a double precision floating point number, and it actually uses 52 bits to represent this fraction instead, and 8 bits to represent the exponent. So it just takes up about 4 times more logic gates in order to record this number or do computation, so everything gets bigger by a factor of 4 in order for it to do the same thing with double as opposed to half precision floats. Okay, I think that's the technical word for it. In this class, we're going to deal with integers only, just so that we don't have this additional translational error layer. All the math works exactly the same in binary. It's just when we have to translate to decimal, that's when we have to do this little exponents and fraction mapping. Okay. All right. So let's talk about unsigned integer first. We're going to deal with the signed right after this. Okay. As we said, right, unsigned integer, we're going to transcribe this from right to left. So this number 1 represents 1 times 2 to the 0 power. Right. That's what this translates to. The next one translates to 2 to the 1 power. The next one translates to 0 times 2 to the 2, which is actually 4, and then you have 8 here, right? You add these number up. That's how you convert it to decimal, which is what will make sense in our head. Okay. The leftmost bit here, I'm going to circle this in red, right? It's called the most significant bit, or the MSB. When we get to signed integer, that's going to actually turn into the signed bit. And you can say, well, that's probably the most significant thing. Also, if you have, positive $1 million versus negative $1 million, that's a huge difference, right? It's actually very significant. We're going to see how that turns out. But the left bit is always called the most significant bit. And if it is a signed integer instead, then it'll be the one next to it. That's called the MSB. Okay. The rightmost bit, let's do that in green, right? This one is the least significant bit, the LSB. Okay, and there's stuff between them. Okay. The reason we're going to call these out is because it's actually, if you were trying to send a number over internet or optics or Wi-Fi or something like that, it's most important to send the most significant bit, because that determines whether or not, in this case, right, the number 8 versus 0 makes a bigger difference, bigger contribution to 11 than the least significant bit, which is actually contributing 1 and 0, right? So if you got the most significant bit wrong, right, you would get a 3 instead of 11. That makes a big difference. But if you get the least significant bit wrong, then you get 10 instead of 11, which is, it's still, you don't want that error, but it's not as important. Okay. There are also other ways to represent binary numbers, especially when you're translating to decimal display all the time, which is what we're used to. The way they do this is by basically storing chunks of 4 bits information, and each of these 4-bit information represents a number from 0 to 9. But right away, hopefully you see that this is actually wasting 10, 11, 12, 13, 14, and 15. So you're wasting 60% informations are wasted. So this is called binary coded decimal. It's useful when you have to display these numbers in decimal, but that's the really only use of it, because you're wasting like 60% of the storage capacity in your gates. Okay. There's also hexadecimal, which is very similar to binary coded decimal, but then you don't waste that 6. So the way you do this is that, well, you count from 0 to 9 normally, but then, right, instead of writing 10, because you're not allowed to have, 1 0 that takes 2 places instead of 1, right, you put A, B, C, D, E, F. So those are the next 6 numbers, right? So the letter F actually represents a value of 15. Okay, so for example, and the way I know the book doesn't mention this, the way that most hexadecimals are represented is you put a 0x in front of it. Why 0x? But that's just a convention that people started using probably in the 1960s, and then it's too late to change it now. Okay, 0xa, right? A actually represent decimal 10, right? So that's why 0xa is 10, 0xb is 11, right? If you put 0xba, right, the B, right, actually means 11, but then its place, right, instead of being 16 to the 0 power, is 16 to the first power. So you have to multiply that together, okay? And then the A represents 10 once again, 10 times 10 times 16 to the 0, right? Any power, anything to the power 0 gives you 1, right? That gets you 10. So in decimal, that number is actually 186. Okay. So when you see this, when we start doing some translation between them, you'll be familiar with it. Okay. Okay. So how do we deal with signed integer? Okay. Right. As I said, having a positive $1 million versus a negative $1 million is a big difference. So we need a way to represent that, right? As I mentioned before, well, why don't we just use the first bit to represent the sign? Okay. So this is an example here from the book, right? So let's say you have 0001 in binary, right? That means positive 1 in decimal. If you want to represent negative 1, right, you flip the sign bit, right? So essentially what's happening is that these three are gives you the magnitude, and then the first bit gives you the leftmost bit gives you the sign, whether it's a positive or negative number. The problem is the math doesn't work here. Okay. Okay. Now we're going to go back to grade school. Okay. If we add these two numbers together, right? +1 plus -1 should add to 0, right? Going back to the way we add, right? We line these things up, right? Remember this, right? You add them together, right? 1 plus 1 gives you 0 with a carry of 1. Looking, sounding familiar, right? So 1 plus 0 plus 0, that gives you a 1, right? 0 plus 0, there's no carry there, so it's 0 plus 0, so this way. So, right, but if you convert this to decimal, right, this convert to, well, it's a negative number because we have a 1 in front, but this is the 2's place, it actually gives you -2 in decimal. Okay, obviously 1 plus -1 does not equal to -2, okay? This is why we need to do this system called the complement instead, okay? When you do a complement of something, it's not that you're saying that they are, actually they even spelled differently. A complement of something is that if you see a 1, you switch to a 0. If you see a 0, you switch to a 1. So you're kind of getting the opposite state, okay? So once again, we go back to our example where, oh, well, if the number is equal to, if this signed integer is 0, 0, 0, 1, right, represents +1 in decimal. The complement of that is that every time I see a 1, I put in a 0. Every time I put in a 0, I get a 1, right? And what's neat about this is that, right, the sign bit flips correctly all the time, right? This is nice. Okay, so I know it's a negative number. I don't have to worry about which bit I'm flipping for the sign bit. I always know that if I complement a number, it always flips it from a positive number to a negative number, or negative number to a positive number. Okay, and this number is going to represent -1 instead. But before we do that, we're going to see. I'm going to tell you why this happened. We're going to add 1 to it. Okay, so this is just this is known as the 1's complement. Okay, and today's computers actually uses this system called 2's complement, named maybe after me, right? This actually predates me. Okay, so 2's complement, though, what you do is once you have the 1's complement, right, you add 1 to the number. Okay, why would you do this? Okay, we'll see. Okay. So the 2's complement of -1 in decimal, right? It's actually 1, 1, 1, 1. Okay. And now let's see what happens when you add these numbers together. Okay. So okay, 0, 0, 0, 1, and then 1, 1, 1, 1. I'm going to add these numbers together. Right. 1 plus 1 gives you a 0 with a 1 as a carry. 1 plus 1 gives you a 0 with a 1 as a carry. And 1 plus 1 gives you a 0 with a 1 as a carry. And then once again, you get, okay. So there's a carry over here, but since we're dealing with a 4-bit number, that actually just gets thrown away. You never actually hold it in your device. Okay, it just kind of gets ignored. Okay. All right. So, and then, well, of course, 0, 0, 0, 0 is 0 in decimal also. And now we are getting the right answer. And I'm going to have you guys play around with this a little bit in the pre-lab, and that way it shows that it does work. Okay. So this is just a table of some decimal numbers up to 7 with the 4 bits, right? That we can represent with 1's complement. So remember that when you do the binary version of it, so this is the positive value, right? 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, that represents 2, and then 0, 0, 1, 1, right? To represent the negative value of it, what you do is you go to do the 1's complement first, so it's a 2-step process. you flip all the bits, okay? The second step, we'll do that in yellow then, is you add 1 to it, okay? Right, I just add 1, I add 1, right? If I add 1 to this, right, it carries over to the 2's place. That's why it's like that, right? And I'll have you guys play around with this table also, and that way you get used to these 2's complements and know how they actually work. One thing to note is that in the 1's complement play situation, this is why we had to switch from 1's complement to 2's complement. The binary number for 0 is represented by 0, 0, 0, 0. The binary version of -0 is represented by 1, 1, 1, 1. The math still works. The problem is that now you have 2 different binary states that represents the same value, and that messes the math up once in a while. Okay. In fact, this is such not, you have to program around it. So if you have a positive 0 versus a -0, or actually if you have a -0 instead of a positive 0, what people do is they just have to always flip that. So just flip all the bits so that it's actually a positive 0. This was actually used until 1980. This UNIVAC 1180 still is the last machine that uses 1's complement. And these are probably in museums now. The 2's complement was actually first introduced in 1972. So very, well, at least to me, very recent. Maybe for you guys, it's like ancient age. These are still vacuum tube computers. But the reason we have to do the 2's complement as opposed to the 1's complement is because we don't want to deal with having 2 different zeros, okay? And by doing the 2's complement, you actually just get rid of any possibility of getting a -0, okay? All right. So, let's see. And that's the lecture for introducing you guys to binary numbers and binary electronics. And next lecture, we will see how we actually implement these on circuits.